A very good morning to everybody. This is Dipen Saha, postgraduate part-time student of October 15 batch, and I have been working as junior engineer at Coast Port and Estuary Management Division in Institute of Water Modeling since 2015. This is short introduction about me. I hope all of you are in good health in this COVID-19 pandemic situation. I welcome you all to my thesis presentation. The title of my thesis is Estimation of Longshore Sediment Transport and Shoreline Evolution along Kuakata Beach by Numerical Modeling. My thesis supervisor is Professor Dr. Mohammad Ataur Rahman, Department of WRE BUET. This is the outline of my presentation. I am going to cover the specific topics throughout my presentation. These are background of the study and study area, scopes of the study, and then objectives of the study, literature review, then methodology and data collection, and after that analysis and result. Under analysis and results, I will cover all of my objectives of the study one by one, and then conclusion, and last of all, recommendations. First of all, background of the study and study area. This is the map of coastal zone of Bangladesh. There are 19 districts under coastal zone. 32% of total population lives in the coastal region. Bangladesh has 710 kilometers of coastline. Kuakata, which is also known popularly as Sagar Khona, is located on the coastal zone of Bangladesh. One can enjoy both sunset and sunrise from Kuakata. Kuakata Beach is at Kolapara Upazila under Patuakhali district. Kuakata is the second largest attracted beach in Bangladesh. It is very important place for tourism, hence it plays vital role for national economy. Beach erosion is becoming serious problem day by day. Some areas have serious erosion and some areas are accreting with time as well. Erosion mitigation measures already taken by BWDB in some places. In the picture we see tube and bag are used to protect the beach from erosion. The Kuakata is 320 kilometers south of capital city Dhaka and 70 kilometers away from Patuakhali district headquarters. The area lies between latitudes 21 degree 48 minute and 21 degree 55 minute northing, and longitude 90 degree 3 minute and 90 degree 15 minute easting. If Kuakata Beach can be developed properly, it could be one of the world's most unique beaches. There are 139 polders all over the Bangladesh, especially in coastal zone. These polders were constructed in the early 60s to protect the area against tidal flooding and salinity intrusion to boost up agricultural activities inside the polder. Kuakata is under polder number 48, which is shown by red circle in the map. I have downloaded this video from the Google Earth engine. From this video, we can see that the western side of Kuakata is eroding and the eastern side is accreting with time. Our main concern is about erosion, and we need to address this with proper measures to save the beach. We are seeing some photographs of Kuakata Beach. First two photos reflect the erosion problem of the beach, and third photo shows the human chain to save the Kuakata, and last photo shows the natural beauty of Kuakata. These photos have been collected from newspaper published in different time. Now, scopes of the study. Under scopes of my study, I will explore, and I have studied nearshore wave tide hydrodynamics, which has been simulated by hydrodynamic wave model, and current rows and wave rows have been made from the result file of hydrodynamic and wave model result, and it has been identified whether longshore or cross-shore current is dominant, and historical satellite images will be analyzed to understand erosion, accretion, and shifting of coastline. Eventually, longshore sediment transport will be estimated, and last of all, coastline evolution will also be seen and validated with satellite image coastline for a particular year. Now, objectives of the study. I set 4 objectives in this study. These are as following. To assess the shoreline change along Kuakata Beach from historical satellite images. I have collected the satellite images from 1978 to 2020. And my second objective is to set up, calibrate, and validate hydrodynamic and wave model of Mike 21 FM and Mike 21 SW, and simulate the nearshore wave tide hydrodynamics to estimate longshore sediment transport rate using Litdrift model for the study area. And last objective of my study is to simulate the shoreline evolution along the study area using Litline model, which will be verified with real-time coastline position for a particular year. Now the literature review. Literature review is very important prior to conduct a study. I also went through a number of previous literatures, mainly bankline or coastline shifting study, hydrodynamic and wave model related study, and coastal sediment transport related study, shoreline evaluation related study. I studied several journal papers, conference papers, MSc thesis, scientific documents, and consultancy reports. I'm going to discuss some of them. A study titled Coastal Hydraulic and Design of Protection Measures for Marine Drive Road was conducted jointly by IWM and BUET. Bay of Bengal model is used for hydrodynamic part, and longshore sediment transport was estimated 5 lakh meter cube per year for beach along the Marine Drive Road, and required protection measures were also devised in this study. Another study by my supervisor, Dr. Mohammad Ataur Rahman, and other co-authors titled Investigation on Erosion of Kuakata Sea Beach and its Protection by Artificial Beach Nourishment, published in IAV Journal. In this study, coastline shifting assessment is done using satellite images of 1973 to 2010. By Dean's method, they also found different volume of nourished sand for different grain size. They also calculated half-life of the nourished sand, which is 4.5 years. Rajab and other co-authors studied on Puducherry coast of India. They estimated longshore sediment transport month-wise based on empirical and process-based method. Under empirical method, they used Stark, Camfuis, and Van Ryn formula. And on the other hand, under process-based method, DHI Litdrift model was used to estimate annual littoral drift for the coast. Hendriano and other co-authors published a journal paper titled Modeling of Sediment Transport Affecting the Coastline Changes Due to Infrastructure in Bathang's Central Java. In this study, 4 years web climate is used and literal drift model simulated for 4 years as well. Longshore sediment budget is estimated for 4 transects and got different value for each transect. IWM conducted a study titled Feasibility Study for Protection and Development of Kuakata Sea Beach in 2020. In this study, consultant has done HD and web model for the study area and suggested series of groin based on HD and web model result and other interventions for the development of Kuakata Beach. 2 options have been devised to protect the beach from erosion threat. Under option 1, series of groin and multifunctional dike, and under option 2, slipping defense, coastal armoring, sand nourishment, and multifunctional dike. Finally, by multi-criteria analysis, option 1 is selected as best suitable option. Now, if I want to summarize the research gap from the literature review, it would be like detailed shoreline shifting assessment is not done with latest available satellite images. Longshore sediment transport estimation is not yet done using Litdrift model for Kuakata Beach. Coastline evolution is not observed yet by Litline model for Kuakata Beach. Now I will be talking about methodology and data collection. This is the outline of the methodology. This flowchart represents the methodology of my research work as a whole. First of all, from background analysis, we selected Kuakata as our study area. Then literature review relevant to my study, data collection, and develop and set up a dedicated hydrodynamic model for the study area, which derived from calibrated and validated BUB model, that is Bay of Bengal model. Then calibration and validation of hydrodynamic model, and develop and set up a dedicated web model where HD result file is used, hence it is called coupled with HD model. Then calibration and validation of web model. Finally, setup of Litdrift and Litline model using the HD and web result from where we get annual littoral drift and coastline evolution. Different types of data have been collected for this study: bathymetry, satellite images, water level, discharge, 1D HD result file, web data, wind data, and sediment properties are the main data of my study. This is the simple data collection matrix, and water level, discharge, and web data have been collected from IWM, satellite images from USGS, web field and wind field from ECMWF, that is European Center for Medium Range Weather Forecast, and sea bathymetry from JEPCO and river bathymetry from IWM. Observed water level data at Kuakata and Kuakata collected for calibration and validation of HD model. Tidal difference at Kuakata and Kuakata are 2.5 and 3 meter respectively. Discharge data at Tethulia and Vishkali River have been collected for the year 2017 and 2015 respectively. Just to understand the wind pattern of Kuakata study area, wind data usually consists of wind velocity and direction, has been collected from BMD, that is Bangladesh Meteorological Department, for a year. And we can see from the wind rows that most of the time wind blows from the south to north. This is the wind field collected from ECMWF for BUB domain for 2008 to 2019 with 0.125 degree resolution. and other informations you are seeing here in the right side. Satellite images from USGS, which are of 30-meter resolution. These Landsat satellite images have been collected for dry season and low tide time, now, which is prerequisite for coastline shifting assessment. I collected long-term 1D result file of Southwest Regional Model, and it is required for the boundary of 2D model. This is the web data measured 24 km offshore of Kuakata in connection with LNG terminal project of IWM. I use this data set for the calibration of web model. This is the web field data covering BUET domain collected from ECMWF. The depth integrated incompressible Reynolds Everest Navier-Stokes equation, which are the governing equation of 2D hydrodynamic model. This consists of local continuity equation and two horizontal momentum equations, which are mainly partial derivatives. This is the simple flowchart of hydrodynamic model. For HD model, we need to provide bathymetry and bed resistance as input data. We need to define boundary condition. For upstream discharge is given, and for downstream water level is given. We calibrate the model changing the Manning's M or bed resistance value. We get water level and discharge and current speed and reaction as output of the model. This is the conservation equation, is the governing equation for wave action. This is also a differential equation. And this is the simple flowchart of wave model. Here seabed topography and riverbed topography are used for the domain. Wind field is given as input for the domain. Wave model is coupled with HD model as water level condition is given from HD model result. Boundary condition is given from the wave field. The calibration parameters of wave model are bottom friction, braking parameters, white capping, etc. Significant wave height, peak wave period, mean wave direction are the main output of wave model. Litdrift model has been developed based on these differential equations like current computation equation, vertical turbulent diffusion equation, and equations for suspended and bed load. This is the structure of Litdrift model. Sediment data is one of the inputs of the model. D50 value is collected from previous literature. Moreover, spreading coefficient and specific gravity of the sediment are assumed based on other reports. Wave climate for 4 years also given as input, which has been derived from wave model. A wave climate consists of significant wave height, peak wave period, mean wave direction, and reduction factor, which essentially a time series. Bathymetry data for each transit is to be provided. Sediment transport program works on the input data, and we get time series on littoral drift as output. Finally, we calculate littoral drift from the time series. Coastline evolution model or Litline model is based on the continuity equation of the sediment volume, which is the partial differential equation. This is the simple flowchart of Litline model. At first, littoral drift transport table is to be generated, which is basically a .bal file. Detailed procedure is given in this write-up, in the thesis write-up. In Litline model, setup is domain. In Litline model, setup, a domain is to be given. Initial profile series or coastline is given as input. Moreover, cross-shore profile, wave climate derived from wave model, littoral drift transport table, etc. are also given as input. We get position of coastline as a time series, which is the output of this model. This model calibrated and validated with satellite image shoreline. Now I'll be talking about result and analysis of my thesis work. I will cover all of my objectives one by one. First objective is coastline shifting assessment using satellite images. Kuakata beach can be broadly subdivided into three areas such as Lebu Shore, Gongamoti Shore, and Kawa Shore. Lebu Shore is erosion prone, whereas Kawa Shore is inclined to deposition, and the length of total coastline of Kuakata is about 24 kilometer. As we see in the right map, where the coastline is subdivided into chainage for convenience of analysis. For coastline shifting, satellite images from 1978 to 2020 are used, especially for the year 1978, 1988, 1998, 2008, 2018, and 2020. First 5 images are of 10 years interval and last 2 years are 2 years interval. All are georeferenced images. By USGS tool, coastline is digitized carefully for each year. We see in the left map that western side coastline is moving in towards land in course of time. So the side is facing erosion threat. On the other side, the eastern side, the coastline is moving towards the sea with time. So accretion is happening here. In the middle portion of the beach, about 4 kilometer is more or less stable. Sometimes it erodes and sometimes accretes. I got from the analysis that up to Chainage 13 kilometer, the beach is erosion prone, and 13 to 70 kilometer Chainage, it is more or less stable. And from Chainage 17 to 24 kilometer, that means 6 kilometer coastline or beach is accreting. I quantified the erosion and accretion area by GIS tool. To do this, two coastlines for the year 1978 and 2002 or 2020, whatever, are superimposed and erosion aggregation area has been found out. We see from the right map, erosion area is 4.8 square kilometer, whereas accretion area is 3.7 square kilometer. This amount of erosion and accretion occur in 42 years over 24 kilometer long beach. As I mentioned earlier, the shoreline is subdivided into chains for convenience. There are 24 segments, and for each 1 kilometer, and each is 1 kilometer in length. In each chainage, shoreline shifting is measured for long term, that is 10 years by GIS tool. For this table, I calculated the average erosion and accretion of Kuakata beach. So the average erosion rate and accretion rate are 9 meter per year and 12.2 meter per year respectively. Now objective number 2, development of hydrodynamic model and wave model for the study area and nearshore hydrodynamics. I developed a dedicated model for my study area, both for HD, that is hydrodynamic, and wave model, because it reduces simulation time remarkably. In the left, we see the domain of BUB model. My dedicated domain is shown here by red box. Numerous rivers are in my dedicated domain. For instance, Bishkhali, Burishore, Boleshore, Andarmanik, Rabnabad Channel, and Tetulia, and Hilsha. There are 4 boundary conditions for this dedicated HD model. Upstream boundary is given as discharge time series at Hilsha River. As I mentioned earlier, from Southwest Regional 1D hydrodynamic model result file, this upstream boundary is extracted, and other 3 boundaries, that is south, west, and east, These boundaries have been generated from global tide model. Actually, this is a built-in module in Mike. Based on tidal constituents, water level is predicted by this model. We can generate time series of water level for any time on the sea by global tide model. To make mesh file of bathymetry, at first we have to work on grid generation. In Mike, we use MDF file to do it. Both quadrangular and triangular mesh are used in the dedicated domain. In sea estuary, uh, and wide channel, triangular mesh is given, whereas on the uniform and narrow channel, quadrangular mesh is given. Near Kuakata Beach, especially up to 3 km offshore, very fine mesh is used. In the other part of the sea, coarser mesh is used. I updated the bathy data for Rabnava channel, lower part of Bishkali, Buri Shore, Andarmanik River. This updated bathymetry data were collected from IWM, collected by IWM in 2019 in connection with the nuclear power plant project in the southern part of Bangladesh. For C, I used JEBCO bathymetry data. By interpolation of scattered data on MDF file, mesh file of bathymetry data, bathymetry is created for the dedicated domain as we see in the left side. On the right side, this is the Manning's map for HD model. Calibration and validation of HD model. I have calibrated the hydrodynamic model for the year 2017. For water level and discharge and water level calibration locations are Kuakata and Kawachor. We can see observed water level and simulated water level matched well. I calibrated the discharge at Tethulia River located in Tamchor. Measured discharge and simulated discharge matched here also. I also validated the model for the year 2015 for water level and discharge as well. Water level validations locations are Kuakata and Kawachor. Discharge validation for the year 2015 at Bamna in Bishkal River. We can see validation curve is also satisfactory. A dedicated web model was set up for my research work. Same domain of SD model is used here. We have to provide web data time series for boundary condition. Here are 4 boundaries in the upstream Hilisha River. Closed boundary is given, web action is not present there. Boundaries for south, west, and east are extracted from the BUB web model result file. I calibrated the web data for the year 2018 in the 20 km offshore from the Kuakata beach. Main calibration parameters are alpha and gamma coefficient, white capping, and bottom friction, etc. From the wave model result, using significant wave height and mean wave direction, wave roses are prepared, and 3 wave roses are shown here. One is near transect 2, one is near transect 4, another one is in transect 6. Actually, these transects are set for finding littoral drift. So we can see most of the waves hit the beach rightward angle, which essentially means there will be a longshore sediment movement, and it will be in eastward direction. Current analysis has been carried out for 2 periods like monsoon and dry. For every period, water level was found out. 4 points have been identified in water level hydrograph. Basically, these are transition points that can happen in a day. Point 1 is identified as when water level move from low tide to high tide. Point 2 is identified as when water level is in equilibrium condition, that is low tide to high tide. Point 3 is identified as when water level move from high tide to low tide, and point 4 is identified as when water level is in equilibrium condition, high tide to low tide. And current speed and direction for monsoon period is shown in the left side. And This is for dry period in the right side. In all cases, it is observed that for point 1 and point 2, current direction is rightward. On the other hand, for point 3 and point 4, current direction is leftward. This is due to the presence of tide action over there, but it is also observed that current speed is higher in east direction compared to west direction, so longshore sediment transport occurs left to right. Current rules are also prepared from the result of coupled hydrodynamic model for the study area. This current rules is in left portion of the beach, which is marked by red dot on the map. Here, rightward current is dominant. This current rose is for the middle portion of the beach. Here, current is in the both direction, but in rightward direction, current speed is higher. This current rows indicate that most of the currents are slightly angular to left direction in a year. We'll see later there will be very little annual drift leftward. And these diagrams are with wave action. I mean, here SD model is coupled with wave data incorporating wave radiation stress. By analyzing these diagrams, we can conclude there are two-way current in Kuakata nearshore, but current speed is higher in flat tide, which cause littoral transport from west to east. My statistical analysis tool of my data view manager, maximum current speed, maximum bed shear stress are found out. Bed shear stress increases with the increase of current speed. Moreover, it is also seen as we go offshore, current speed and bed shear stress increases. From this table, we can see maximum current speed and maximum bed shear occurs at monsoon period with wave and flat tide condition. This condition actually governs for longshore sediment transport. Now I will be discussing about objective number 3, estimation of longshore sediment transport using littoral drift model. There are 6 transects we can see in the map, which are located 4 kilometers away from each other, covering the whole beach. Transects are on Chainage 3, 7, 11, 15, 19, and 23. As we see in the right map, the length of each transect is taken as 2 kilometers. All transects are perpendicular to the coastline. Bathymetric profile on each transect are extracted from the BUET bathymetry by data extraction tool of Mike. 6 bathymetric profiles are shown in the graph. Slope varies from 1:100 to 1:200, and grid size is taken as 5 meter. Wave climate is extracted at the end of each transect from the wave model result file. Wave climate is nothing but the time series of significant wave height, peak wave period, and mean wave direction, and another column is added in the time series named reduction factor, which is assumed as 0.75 required for Litdrift model. It is found from previous literature that the median size or D50 value of beach material varies from 0.17 to 0.21 millimeter. I use D50 value as 0.2 millimeter. Geometric spreading factor is assumed that 1.5 based on Marine Drive project of IWM and BUET. Nickert's roughness coefficient is considered as 4 millimeter. These are all input data. For better result, Litdrift model should be simulated at least for 4 years. I prepared the wave climate for the year 2015 to 2018. So simulated period is also from 2015 to 2018. Finally, I got the literal transport for each transit, and longshore sediment transport is different for each transit as erosion accretion process is dominated there. For first four transit, I mean for transit 1, 2, 3, and 4, which lie on western side of Kuakata beach, annual littoral transport is higher, and whereas for the last two transit, littoral transport lower comparatively and occurs in opposite direction. As you see in the map, the values are shown in the map. We got different longshore sediment transport rate for different transit. In the eastern transits, we got lower littoral transport rate compared to western transits. In transit 1, longshore sediment transport is 69,463 meter cube per year, and in transit 2, 1,33,000 meter cube. So in between transit 1 and 2, there will be erosion, which amounts 63,000 meter cube per meter cube. And similarly, in other segments, erosion and accretion occurs. Maximum deposition occurs in between transit 4 and 5, which amounts to 26,000 meter cube in Kawacho area, which has good agreement with the satellite image erosion accretion analysis. Total erosion is 0.14 million meter cube, and total accretion is 0.236 million meter cube per year. The most accurate way to verify longshore sediment transport is using bathymetric survey of different year. In the vicinity of Kuakata Beach, I have bathymetric data of 2007 and 2014. By superimposing of these years data in GIS by cut fill method, erosion accretion volume are calculated. From bathy data, I got total erosion in 7 years is 1.3 million meter cube, and accretion is 1.5 million meter cube. We see from this table model simulation erosion accretion volume is manipulated. Accretion volume is multiplied by 7 to compare with the volume found from bathymetric data. So erosion accretion volume in 7 years from simulation are 1.03 million meter cube and 1.65 million meter cube. We see the simulation accretion value is higher than the bathymetric data volume, but close to it. On the other hand, erosion is lower than the bathymetric volume. There are different formulas are available to estimate the longshore sediment transport, like SARC formula, Camphis formula, and Van Ryn formula. In my study, I estimated SARC formula and Camphis formula and bathymetric changes as well. And there are the main formulas by Coastal Engineering Research Center, that is SARC. Detailed calculation procedure is given in the main thesis write-up. Here, K is found from the graph, which depends on D50 value. Other parameters are found from the wave model results and analysis, and we get literal transport is 1,42,000 meter cube per year. Another popular formula is Camphis formula. Using this formula, we get a literal transport is 1,27,227 meter cube per year. Near transit 2, simulated longshore sediment transport is 133,136 meter cube per year. We can see in the bar chart that simulated literal drift transport value is almost equal to literal transport found out by other method near transit 2. Now I will be discussing about the last objective of my thesis, and that is the simulation of shoreline evolution by Litline model. As erosion is our main concern, Litline model is set up only for erosion prone area. I mean, in the western side of Kuakata beach, we need to set a baseline which is marked as yellow line in the figure, an initial coastline position from the baseline is to be provided, which is a DFS1 file with 100-meter grid step. This initial coastline, as you see in the map in black color, a dot bell file is also given as input, which is found from Litdrift table generation. And profile information and sediment transport properties are required to generate a .val file. Height of active beach and active depth are also given as input. In the figure, the red one is simulated coastline. And the initial coastline is 2010 and the simulated coastline is of 2018. 9 years of web climate for the year 2010 to 2018 is used in the Litline model. This model, this web climate is derived from the web model. The output of the model gives the shoreline position with respect to baseline in every time step. This model is calibrated with the coastline found from the satellite image for the year 2018 and validated as well for the year 2015. The red line is simulated coastline and the black line is satellite image coastline. We can say they matched well and we get a satisfactory result from the simulation. This is the simulation result represented in the graph. There are 9 coastlines on February month of each year. It is found that maximum 113 meter erosion occurs. This area is shown in the figure by circle. In ECM, WF, future wave field and wind field are not found. So we consider or assume that the last 10 years wave climate will remain same. We can predict the future of coastline by this way, and we can observe the beach morphology incorporating structure like groin in this model. This is the main advantage of this model, though I have not done it under this research. I kept it in recommendation. Future shoreline are predicted up to 2024. It is observed that maximum 48 meter erosion will occur in 5 years, and erosion rate is found 9.6 meter per year. Now the conclusions of my research work. If I conclude my research work, following points will come. Around 13-kilometer western side of Kuakata beach, that is Longshore, faces serious erosion, and on the other hand, 7-kilometer eastern side, that is Coastline, accretes over the last 4 decades, which is found from historical satellite images. A dedicated hydrodynamic and wave model has been set up, calibrated, and validated for the Kuakata study area, and nearshore wave tide hydrodynamics have been analyzed. It is found that longshore current governs in the nearshore of Kuakata, and wet season, spring tide, flood tide with wave action is the governing condition for lateral drift. Longshore sediment transport is estimated from lateral drift model. It is seen that annual lateral drift is 132,000 meter cube per year, and westward is 1 lakh meter cube per year. The net sediment transport so thus it can be justified that sediment movement occurs from the Longshore through Gangamati Shore and ultimately deposits in Coastline area. Coastline evolution model simulated for eroding western side of Kuakata beach, and it is verified with real satellite images coastline, where the same wave climate is used as in Litdrift model, which confirms the accuracy of longshore sediment transport estimation. At the same time, future shoreline simulation has been done, where we have seen that the erosion process will be continued in future at 9.6 meter per year. Now the recommendations of my study. As we know, the dominant current direction and wave direction in the Kuakata beach, mainly longshore current occurs here. Groins can be incorporated in the model. Nearshore or hydraulics can be studied after incorporating groins in the hydrodynamic model, or another study can be done by Litline model. By incorporating groins in the Litline model, we can observe the morphology of that area after installing the groins in the system. And Kuakata beach morphology study can be done incorporating series of groins in, I have already told this. And beach nourishment study can further be enhanced using Litdrift model result of this thesis work. And coastal bathymetry has been used from CMAP and JEPCO in the vicinity of Kuakata beach. Better result can be expected if fine bathymetry would be used, and further study can be carried out using fine bathymetry if it is available, of course, and compared with the present result. So these are the references of my studies. And I thank you all for patient hearing. Now you can ask any questions about this research work. I'll try my level best to address your question. Thank you.